Okay, so in order to explain you the plan on the getting the Cahn-Trace theorem in the Heisenberg group setting more efficiently, let me just brush up quickly the theory of the pseudo differential calculus in the Euclidean spaces setting. Okay, so to this end, let me just fix some notations. Okay, so in what follows, let the alpha be the so-called multi-index. So it's the n tuple of the non-negative integers, the alpha 1 to the alpha n, and let x be a point in the Euclidean space. And here we denote to the x to the alpha this monomial, the x1 to the alpha 1, multiplied by the x to the alpha 2, the xn to the alpha n. And here we denote the multiple order, the partial derivatives by this symbol, the dx to the alpha, like this. So here we can write down like this, and so taking the order of the partial derivative doesn't matter because they all commute, at least in the case of the smooth functions. And here the absolute value of the multi-index means the sum of all is the components. Okay, so with this notations, let me introduce you the notion of the so-called the standard symbols. So the space of the standard symbols of degree m, here m is the fixed real number, well, it's the space of the smooth functions on the Rn times Rn, such that for all multi-indices alpha and beta, there is a constant which only depends on alpha and beta and does not depend on the choice of function f, such that, well, if we take the partial derivative of f like this on the left-hand side, and after we take the absolute value of it, then it should satisfy this estimate. Okay, so it's like it has the same behavior as, well, in the case of that m is a non-negative integer, then it means that in the variable psi, it has a same behavior as a polynomial of degree m. Okay, so if there is no partial derivative with respect to psi, then f can be estimated by the polynomial degree m. And if we take the partial derivative, the beta times like this, and then it reduces the order on the right-hand side. So it has the same estimate as a polynomial of degree m in psi, and in x is nothing but the bounded smooth functions. Okay, so that's the meaning of this function space, and we can equip it with some appropriate the topology. Well, it's a matter of the functional analysis. And this is the typical example of such the symbol function. Okay, so if f is a function of this form, okay, so this is a polynomial in psi with the coefficient. The coefficients are smooth functions with bounded derivatives in the variable x. Then this kind of function belongs to the symbol space of degree k. Okay. Okay, so this is the most common choice of a symbol space in the theory of the pseudo differential operators. Okay, so let F be a symbol of degree m. The following this definition, then we define the pseudo differential operator PF associated. Here is a typo with the symbol F by this formula. Okay, here the d bar psi is the normalized Lebesgue measure, the common choice in the Fourier analysis for the normalization matter. Okay, and it can be shown that for any symbol of degree m, the PF is a continuous linear operator from the Schwarz class function space to itself. Okay, and in the case that the symbol f is a polynomial function in psi, then at least formally, then you would be able to see that this pseudo differential operator associated with this symbol is the differential operator of this form. Okay, so here the capital D sub x to the alpha, well, it's defined like this. Here, the partial derivative with symbol capital D is just the usual partial derivative times minus imaginary unit I. Okay, so I think you would be able to see this at least formally, okay, due to the property you learned in the Fourier analysis, okay? So, well, if f is of this form, then, well, after you take the Fourier transform of a given function u and take the multiplication by this function, then, well, as the a alpha x, well, is the independent of the integration variable psi, we can take them outside of the integral, and the multiplication by the monomial psi to the alpha, well, it changes into the partial derivatives of this form after we take the inverse Fourier transform. Okay, so can you see at least formally how this symbol is a usual differential operator of this form? Okay, so in this perspective, we can see that the notion of pseudo differential operator is the notion generalization of the concept of differential operators. Okay, and by adapting this definition in each local chart, we can also define the notion of pseudo differential operators on manifolds, but I won't deal with it for today. Okay, and here I collect the basic properties of the pseudo differential operators. Okay, so if we take the symbol of degree m and another symbol of degree m prime, then we can define the symbol, the f, well, here this sometimes it's called a composition product, because we can get the symbol f sharp g with degree m plus m prime with this property, which says that if we take the composition of the pseudo differential operator of order m and order m prime, we get another pseudo differential operator with order m plus m prime. Okay. Okay, and
quick question.
Yes.
I would assume not, but does sharp commute? What's the relation to F sharp G and G sharp F generally?
Well, in general, we cannot expect they commute, because well, how can I put this? Well, in general, if we even in the case of two differential operators, they does not commute in general. Do you see what I mean?
Yeah, absolutely. I'm just wondering if there is a clear
yeah.
relationship or if it just really is, okay, that's fine.
Well, yeah. Actually, I omitted the formula, but we can also write down the explicit formula of this symbol function in terms of the f and g.
Okay.
Yeah.
Thanks.
Yeah, of course. Well, it involves the integral of f and g, but in general, the f and g might not be integrable in Kusai depending on its degree. So the general definition of this product symbol involves a technique so-called oscillatory integral, but well, I think we don't need to go into the detail of that kind of things for today. Okay, so another general property of the pseudo differential calculus is that, well, one important reason why we consider the notion of pseudo differential calculus is that, well, actually the studying the operators on the Hilbert space itself is usually quite the delicate and difficult question. So the most important reason why one studies the pseudo differential calculus is that, well, it enables us to interpret the analytic properties of the operator in terms of the properties of function. So here usually we write down the required properties of the function. We take it into account as the definition of the symbol space. Okay, so here is well, this is the most typical result connecting the property of the function and the associated pseudo differential operators. Okay, so for example, if f is a symbol of degree 0 according to this definition, then it's well known that the associated pseudo differential operator yields a continuous linear map on the L2 space on Rn to itself. Okay, and if the symbol satisfies the better decay, then we get a pseudo differential operator with the, how can I put this? Yes, the pseudo differential operator with the better. I just have to forgot the name. What was it? Better associate. Yeah, sorry, the associated singular value sequence. So yeah, so if the symbol satisfies the better decay, then the singular value sequence of the associated pseudo differential operator also has better decay. So this operator itself belongs to the better Schatten ideal. Okay, so if, well, I explained you the ideals which belongs to the space of bounded linear operators on the Hilbert space. Okay, so if the pseudo differential operator is associated with symbol of degree less than minus n over 2, then this operator belongs to the L2 ideal. Well, it's called sometimes it's called the ideal of the Hilbert-Schmidt operators. And if m is less than minus n, then associated pseudo differential operator belongs to the ideal of trace class operators. And if the order of the pseudo differential operator is equal to minus n, then the associated pseudo differential operator belongs to the ideal of weak trace class operators. Okay, so this, as I told you, this is the starting point of the study of the Kahn's trace theorem, because the Dixmuir trace are the linear functionals on this ideal. So if we find out any operator which belongs to this ideal, then we can think that enables us to think about taking the value of the Dixmuir trace of this kind of operators. Okay, so the starting point of the studying Kahn's trace theorem is that we need to find out the appropriate space or class of pseudo differential operators which belongs to the ideal of weak trace class operators. Okay, so let me just give you the basic idea of the proof of the statements like this in the proposition 3.6. Okay, so in the Euclidean space, let the P be the less than or equal to 0, and the spectral theory of the flat Laplacian on the Euclidean space, it's very well known. Okay, so we can figure out the behavior of the eigenvalue sequence of the P's power of the flat Laplacian. And so the given P, we can find out the appropriate ideal J of the ideal of the algebra of the bounded linear operators on the L2 Rn, such that the Laplacian to the P belongs to J. So, in some cases, J might be the one of these ideals, or the other the ideals formed by the Calkin correspondence I mentioned you last month. Okay, so, and as the Laplacian is a differential operator of order 2, we know that the Laplacian to the P is a pseudo differential operator of order 2P. Of course, this also involves some analytic arguments in the pseudo differential property, but I think at least conceptually or formally you can see this. Okay, so how can we prove the ideal property of the general pseudo differential operator associated with a certain symbol? So let P be a pseudo differential operator of order 2P associated with certain symbols. So this is a operator created in this way, associated with the symbol satisfying this estimate with order 2P. Okay, then we know by the composition property in the proposition 3.5 that as this is a pseudo differential operator of, I think I made the mistake here, because I think this should be replaced by minus I'm sorry, just a moment.
It's just minus P, right? You
Minus P, right, minus P, sorry. So as the P is a pseudo differential operator of order 2P, and let's replace this minus 2P by minus P, sorry about that. So as this have the order 2P, and as this has order the minus P, by using this proposition, this guy is a pseudo differential operator of order 0. So it belongs to the space of the bounded linear operators on L2 Rn. Okay, and I think at least formally you can also see this formula. Okay, and well, so as we know that the Laplacian to the P belongs to, well, let's assume that the Laplacian to the P belongs to a certain nice ideal, okay? And it's a pseudo-differential operator of order 2P, okay? Then, well, as this belongs to the ideal J, and this belongs to the space of bounded linear operator, then by the ideal property of J, we can say that how this the multiplication operator, and namely P belongs to the same ideal. Okay, so here my point is that one should find the very nice Bayesian building block operator whose the certain power belongs to the desired ideal J. Then by using this trick, we can say that all pseudo-differential operators with same order with this pseudo-differential operator, they all belongs to the same ideal. Okay, so in order to prove this kind of result for the general pseudo-differential operator, to start working on Kahn's trace theorem, so it is important to get one basic model, the building block operator, whose the certain power belongs to the desired ideal. Okay. So, yeah.
Sorry, can I interrupt you?
Yeah, sure.
Yes, I wanted to ask if that connected composition is unique in some sense, or is it? I mean, in that F connected composition G, is it some kind of universe or okay?
Yeah. Well, how can I say that? Yes. Well, I'm also here cheating in some sense. The one can perturb this operator, this function by some other non-zero function in the pseudo-differential series. So here I'm cheating a little bit. So it's unique up to a perturbation of some very nice function, but here I'm omitting that detail.
Oh, okay, thank you.
Okay, so all right. So how can we do all this argument in the case of the Heisenberg group? Okay, so let's start with this way. So here let me first start to mention that there are many other kinds of the symbol spaces in the theory of the pseudo-differential operators. Well, this kind of the symbol space is the most common choice, but sometimes this symbol space does not fit the property required in the problem. So, for example, well, if one wants to work on this kind of symbol, which is the symbol of the Hamiltonian of the simple harmonic oscillator, if you have ever heard about it, and well, this kind of the symbol does not belongs to any of this symbol space S to the M for any M, because this estimate requires the X is the F is bounded in the variable X, but as you can see, this function is not bounded in X, so this definition of the symbol does not meet the desired property in the case of this kind of symbol. So one should find out and apply the appropriate symbol space depending on the problem that you are working on. Okay, so this is the choice of symbol one can find in the literature, so-called the Shubin's symbol class. Okay, right. So now let me tell you briefly my plan on how to work on all this kind of problem in the Heisenberg group setting. Okay, so let's say that I told you that it's important to have the very nice basic model operator. We know very well about the behavior of its eigenvalue sequence, and I think the twisted by Laplacian studied by Dr. Duan's PhD thesis M will play the role of the basic model operator in the Heisenberg group setting, because the behavior of its eigenvalue sequence is well studied in the Dr. Duan's thesis. Okay, so in order to prove the Kahn's trace theorem, then we first need to find out the appropriate pseudo differential calculus on the Heisenberg groups, and to check what kind of the pseudo differential operator belongs to the ideal of weak trace class operators, so we can evaluate their Dixmuir trace. Okay, so we need to find out an appropriate space of symbols. So it should be a space of function satisfying the certain estimate. So we need to find out the space of the function such that they include the twist. They include here is also some kind of typo. Well, as these are the function space, not the space of operators, so we need to find the space of symbols such that this symbol space has the symbol of this operator, not operator themselves. Sorry about this. Okay, and then, well, I think one of the most remarkable result in Dr. Duan's thesis is that he explained that the inverse of M belongs to the two-sided ideal J associated with this Kalkin space. Okay, that's the reinterpretation of the result in the Dr. Duan's thesis. Okay, so we know that by the result in this thesis, the inverse of the twisted by Laplacian belongs to ideal formed from this Kalkin space. Okay, then after we find out the nice symbol space which has the symbol of M, and the nice symbol space which has the symbol of the inverse of M, then we can say that by using the same trick I mentioned here, that then the pseudo differential operator on the Heisenberg group associated with symbol in this class will also belongs to the same ideal. Okay, so we can try to evaluate the Dixmuir trace of such pseudo differential operator which has the symbol with the same symbol space, which has the symbol of the inverse of the M. Okay, yeah. So I'm not sure whether I explained this to you efficiently. So the starting point should be to find out the symbol space which has the symbol of the twisted by Laplacian, and study the pseudo differential calculus associated with such symbol space. But for now, I'm not sure what kind of symbol space I must use to adapt all the strategy already studied in the case of Euclidean space. But I think the pseudo differential theory on Heisenberg group in the literature I wrote here. Then here are the references. The symbol spaces used in the pseudo differential theory in these articles would be possible candidates of the receptacle of the symbol of the twisted by Laplacian. Okay, so after our seminar today, I'll try to find the appropriate symbol space which has the symbol of this twisted by Laplacian, and study the pseudo differential calculus on Heisenberg group associated with that symbol space. So, but I'm not sure about the answer for now. That's all I got for today. And thank you very much for your attention.
Yeah, thank you very much for the great explanation. Yeah, any other comments or questions? So I might add some, not just the comments on the presentation, but it might be better to add something from my presentation then. So if there's no other question, then let me share my screen.
Okay, then I'll stop share my screen.
Yeah, so I just want to be clear what we need to do. So then thanks for our explanation in detail and the direction as well. So I just want to be sure that what we need to try. So let me first start from here. So this is one of the primary reference that we are now looking at, and this gave us the motivation to look at the twisted by Laplacian whatsoever. And the geometry side, by the way, so at least we are motivated to study the Heisenberg group and the sub-Laplacian in various actual perspectives. So this is definitely super important object in mathematics. And all of a sudden, in Sub-Riemannian geometry perspective, some weird operator just shows up, and it seems like it looks something. So that's my current perspective. And at least from this reference, or I could convince is that there is a deep connection between the sub-Laplacian and the associated by twisted Laplacian here. So the one thing that I think we need to understand together is that it's maybe after 24 or wherever. So yeah, let me clarify the notation first. So yeah, so sorry. So because I just want to show you the notation clearly. So the notation of the sub-Laplacian in this dissertation, he just used the curved L. Where is it? I need to find it. So it should be somewhere over here. Curved L. Where is it? Yeah, X and Y are the standard basis of the horizontal distribution. So this is quite familiar form to people in Sub-Riemannian geometry. And then one define, yeah, here you go. So I don't care the sign. So the sub-Laplacian is defined in terms of the square of those two canonical vector fields. So this is just a canonical form of the three-dimensional Heisenberg group, although he wrote as H1, but it's, as I said, it's nothing but R3. And then by using this curved L,
Can I just point out, you're calling them canonical, but if you make an orthonormal transformation on the horizontal distribution, you don't get the same operator.
Yeah, absolutely, you're right. So I'm just saying this is one of the most familiar form that
Okay,
are.
canonical in the sense that it's familiar. Yes, absolutely.
Yeah,
Sorry.
for the comments from the expert. And so from that curved L, we also have the relation with this weird object that now we want to care. So the operator that he defined here is the not curved L sub tau, which is defined in this manner. In local coordinate is written in this manner for the tau parameter here. So this is the operator, and the explanation with the relation between the sub-Laplace and L and this guy is in terms of some pseudo function, whatever that is, so that there is certain relation between the sub-Laplacian and the operator over here. And the bi-twisted Laplacian is just nothing but actually this guy. So unless there is some close connection between the sub-Laplacian and the operator that now we want to look for. And in one hand, so that we first need to understand what this really means. That's one thing that I think we need to be clear. And another thing that I also want to mention is that, so this is the one thing that I asked via the emails. So the one of the canonical example of the pseudo differential operator in the Sub-Riemannian context is the CR, I should say, fractional Laplacian. So, and it seems like the Fourier transform plays a central role in this direction that we want to work on. So I share this document in the Dropbox folder, by the way. So let me try to explain the thing that I care. So this is the same expression as the sub-Laplacian.
Okay.
So one might consider the fractional analog of the sub-Laplacian, and this is indeed the paper that tried to generalize it to the fractional sub-Laplacian and drive the sharp Sobolev inequality in the context of the Yamabe problem in geometry. So there's some context, so-called the Yamabe problem, meaning that one might want to find the constant scalar curvature metric in Riemannian geometry, and one can actually do the same thing in the sub-Riemannian level, so that one can also try to find the sub-Riemannian scalar curvature constant. And naturally there's an operator, so-called a GJMSI operator. I think it's nothing but the some fractional analog of the sub-Laplacian. But anyhow, so what I care is two things. So number one, so there's the Fourier transform. In the case of the Heisenberg group with the sub-Laplacian, so I should, and this is the essential technique in this paper. So there's a notion of the group Fourier transform as the Heisenberg group's Lie group.
Yeah.
So that one can consider the natural Haar measure on the Heisenberg group, and then by using that, one can define the Fourier transform and also inverse of it. And the essential property should be this guy. So we know what this is. So it's there to isometry. So that at least in the case of the Heisenberg group, there is some natural Fourier transform that we can consider in terms of this relation here. That's one thing. And this one is comparable with the sub-Laplacian, including the fractional analog as well. That's one thing. And the reason to consider the comparability with the sub-Laplacian and the twisted bi-Laplacian or whatsoever is that, so there's a clear context to obtain the sharp Sobolev inequality. And this paper also shows that the group Fourier transform that they use in this paper recovers the sharp Sobolev inequality. That's the moral of this paper. And there's a behind geometrical reason. So that's one thing that I just also want to mention. So the key reason to study the Heisenberg group, I mean, in sub-Riemannian geometry is that, so the geometric questions, and philosophically speaking, so whatever geometry that we consider, like the differential geometry, algebraic geometry, simplex geometry, complex geometry, whatsoever, geometric question deeply rely on the classification matter. So we'd like to introduce the necessary structure, and we'd like to classify in terms of that structure. That's what geometers want to do. And in complex geometry, so the one of the model space is the complex hyperbolic space. That's nothing but the Bohr model that I explained last time. And the boundary of the complex hyperbolic space just becomes the Heisenberg group. And in order to say the topological boundary of the complex hyperbolic space is nothing but just a CR sphere, it's just nothing but the odd dimensional sphere. But instead of regarding that as a topological manifold, we want to keep the CR structure on the boundary of the complex hyperbolic space, because the corresponding Dirichlet problem will give the nice rigidity of the complex hyperbolic space. So the CR structure should be considered for the complex manifold as for the boundary. So this is a natural consideration. So that the boundary must be the Heisenberg group for the complex hyperbolic space. And in that consideration, the sub-Laplacian naturally just appears. So where is it? So it looks really weird to consider this. Where is it? Yeah, this is the problem that I today want to just lively explain. So the key reason to consider the sub-Laplacian in the sub-Riemannian geometry connecting to complex geometry is that we'd like to view the Heisenberg group as a CR boundary of the complex hyperbolic space, so that it is natural to consider the Dirichlet problem. So that we already have the boundary data, and then we want to extend the boundary data inside naturally. And the harmonic extension should be one of the natural extension to consider, but that's actually not the case. So it's a very known problem that one can solve the following Dirichlet problem. So that let us start from so you can just think of this M as a Heisenberg group. So that just start from any smooth function on the Heisenberg group. And then this operator, this Laplacian, is the Laplace Bertrand operator on the complex hyperbolic space. So this is just the Laplacian of the Poincare metric, if you want, from the terminology of the complex geometry. So one can try to extend, and this chi has the boundary as just M, as a CR boundary. So this is the complex hyperbolic space as a concrete example. And you can notice that this is just a nothing. So, and this S and M minus S are just some number. So this is just number. So that this is nothing but finding the eigenfunction. So that one start from the boundary data, and then one should be able to extend this boundary data as one of the eigenfunction with respect to Laplacian of the complex hyperbolic space. And those two functions are reasonable enough, and there's some description of the scattering operator, and this is describing in terms of the pseudo differential operator, especially this scattering operator. So, and in order to consider this comparability between the boundary data and corresponding sub-Laplacian and the Laplace Bertrand of the complex hyperbolic space, so the group transform that considered in this paper should be considered in order to achieve the sharp sub-level inequality. So in that sense, this is some of the natural choice to consider the pseudo differential operator theory and the group for transform. That's all I know at this point. So one thing that I can do is that I can try to explain this paper in detail about the CR analog, because at least the operator that they consider is not just the sub-Laplacian, but the corresponding fractional analog. So this is not just the same as a sub-Laplacian, but there should be also the corresponding notion of the twisted bi-Laplacian for this CR fractional Laplacian, right? So this was not investigated from even that dissertation, right? So that there's one more example, and we also need to establish a corresponding space for the pseudo differential operator, as Dr. Lee explained, right? So that I can at least try to study this paper and then try to present if this might be related in terms of the group transform and so on and so on. And so I think we can split the amount of this study in this manner, in a sense that, but I still want to understand more clearly what this really means. So between the sub-Laplacian and the operator here, and then we will eventually get the Dixon-Meyer trace from here. But what's the point in geometric perspective? So if Gianmarco doesn't mind, then I might rely on his study to understand the relation, what this really intuitively really means, and the geometric implication. And instead of studying this one, why one need to study this one? So there might be the certain benefit, but I want to say that more clearly. And I want to establish one more example rather than the sub-Laplacian. And as Dr. Lee already explained, so one can just look at the fractional Laplacian as one of the natural example of the pseudo differential operator, right? So that we already have the certain extension of the sub-Laplacian already, and that context was not considered from the dissertation that we are now looking at. So that if we find the corresponding space of the pseudo differential operator, then we should be also able to extend the non-current result slightly as well. And at least we can try to tackle or take those two objects, sub-Laplacian and fractional Laplacian all together. So how about it? So for my talk from next time, so that then I can try to explain this paper slightly. So how to obtain the sharp sublevel inequality from this paper, and the group Fourier transform was how to they use it, and so that and so on and so on. But this is nothing to do with the twisted by Laplacian. But at least this gives some natural example of the fractional sub-Laplacian that we can also extend.
Can I ask, do you know if people have looked at Fourier transforms on other Sub-Riemannian spaces? Because I've only ever heard anyone talk about it on the Heisenberg group.
So here is currently what I understand. So the analog is always coming from the real hyperbolic space. So if we look at the real hyperbolic space, that just means that this is the complete simply connected Riemannian manifold with the sectional curvature negatively just constant. Then if one look at the topological boundary, then one can just assume the topological boundary just also becomes just an n-sphere. Then one can also solve the differential problem, start from the boundary data and take the harmonic extension in the inside, then this indeed behaves well. So this is a classical theory in geometric analysis. And what people wanted to do is that people want to replace the real hyperbolic space to the complex hyperbolic space. And in order to solve the differential problem, just the topological boundary and sphere was not good enough. So that one need to put the additional structure as a CR structure. And that naturally becomes the Heisenberg group, which is a CR also isomorphic to the just a n-sphere with minus 1 point. So that's the stereographic projection. So but unfortunately, because of the Heisenberg structure is more rigid rather than just the topological n-sphere. So the same method in the case of the real hyperbolic space does not work. So that one need to consider the additional the method to deal with these types of the rigidity. And this one has the limitation. That's actually what I already know. So this is not the case of the general fractional Laplacian. So there is a certain range of this fraction here, because the group Fourier transform only works for a certain range of the fraction here. So that this paper was lucky enough to extend a certain the case, because the group Fourier transform in this case doesn't work enough. And that's why in the appendix of this paper, what they explain is that, so they also wanted to extend the case to the quaternion Heisenberg group and also the other cases, but they didn't know how to do it. So they just extend the case of the complex Heisenberg group in the certain, just a really limited range of the fractions. And just that's all. But still, this is the generalization of the sub-Laplacian still. So that it would be worthwhile to also look at in detail. And also they obtain the sharp sublevel inequality. This connects the Yamabe program to find the constant scalar curvature metric, also in the context of Sub-Riemannian geometry as well. Yeah, so yeah.
Maybe I can also go ahead.
No, you go ahead first, Gianmarco. I'll tell you later on.
I do want to say also the complex hyperbolic space is Kähler, yes?
Yes, absolutely.
So, okay, so I'm not crazy. Do you remember there's this correspondence between Sasakian and Kähler, and then you can pass this down to contact or K contact manifolds and almost Kähler? Is this correct?
That part I should know. I don't know.
This is the presentation that I gave our second year. So
I heard about it, but I never actually look at any reference that relate to that one. I definitely agree with what you're talking about. So like
my point is that if we can find an analog of the complex hyperbolic space, but weaken it so that it's almost Kähler, not Kähler, then I think that I know then the boundary is K contact, but not Sasakian, and thus it's like a perturbed Heisenberg group.
Absolutely. So what I know for sure is that if we start from the complex hyperbolic space, then the corresponding CR boundary should be in fact the complex hyperbolic vibration.
Yeah, I mean in general, whenever you do this procedure for a Kähler manifold, you're always going to recover an actual.
If you replace the field from C to just a quaternion, I definitely just lost what I should do.
Oh, when you go to quaternions, you should get 3 Sasakian.
Yeah,
the boundary should be 3 Sasakian.
Yeah, but there should be.
I think it would be more interesting to talk about 3K Kähler.
Yeah, right. Yeah.
Or 3K contact. Excuse me. 3K contact.
quaternion Hopf vibration and the corresponding quaternion one. Yeah, I that should be the case, but yeah,
Oh,
it's
anyways,
quite scary.
okay.
Yeah. Thanks for the explanation. Yeah, Gihyun, go ahead.
Yes. So let me just try to put Kanhe's exposition in the lively in the one sentence. So you mean that the lively one, it would be possible to improve the geometric result if we adapt some the more the detail, the pseudo differential theory, the whatever, then it would be able to improve the result in this paper, because the analytic tool or the fractional power of the certain operator is limited in this paper. Am I correct?
So let me try to explain what I actually am thinking. So the sub-Laplacian in the Heisenberg group, then there is a notion of the twisted bi-Laplacian.
Okay.
And this is also coming from the not curved L sub tau from the dissertation. And there's a relation between the sub-Laplacian and this L sub tau. So the paper and dissertation says this is the associated operator from the sub-Laplacian, but I just want to understand what this really means. So it seems not clear with me. So I want to rely on the understanding from John Marco, if John Marco doesn't mind. On one hand, so one can extend this L to be fractional sub-Laplacian. And in this case, still one can obtain the sharp Sobolev inequality.
Yeah. So in other words, you would like to rigorously define the fractional power of that curved L.
Yeah. So that I also have, let's say, R sub alpha, for example, then there should be also corresponding M sub alpha.
Okay.
So, and even in this context, we actually hope that there is something new that we can do still, but even we can also generalize slightly, because there's a over here notion of the group for a transform, so that it might be compatible with the pseudo different theory that now we are carrying.
Of course.
And also there is a like the L sub alpha sub tau. I don't know what this is, but so that one can also extend this one slightly, so that we can at least compare those two all together to study and do the research. That's the thing. And at least I can try to study this one. If we care, then I can present something relevant to our project. As
I told you, the understanding the analytic behavior of all this fractional power is also important, also in the perspective of the constraint theorem. But I'll also take a look at the paper you just showed us and find out whether there is anything that also I can do with the result of that paper.
Of course. And at least for this paper, I looked the detail before, so that if we really care the understanding of this paper, I can definitely present from A to Z. I can try to study, but for a moment, so our target is now quite clear, right? So we need to find the space for the natural target first, but there are some necessary candidates, and I need to rely on Gihyun's expertise for that. And so we can just proceed the presentations that we feel it might be eventually helpful.
Okay, then I will try to find out the appropriate symbol space where the pseudo differential calculus, which is a natural receptacle of the fractional power of course, the twisted bi-Laplacian, also the fractional power of the sub-Laplacian considered in the paper you presented. So
of course,
so I think that will help out to understand the necessary analytic details discussed in both papers, the Dr. Duan's dissertation and the paper you have just shown us.
Absolutely. And also, Songbei, as a participant, if you wanna like to study either the corresponding CR geometry or the complex geometry or those spectral like the geometry if you want, then you can definitely present in the seminar. So it's definitely okay. And you already have the lecture note of the Gihyun, so it's also good to also review the detail if you want. It's up to you. Or you can just participate as indigenous participant without the presentation. So yeah, also allow you to do whatever you want.
Okay, let's see.
Yeah, so then let us stop the record and see you after 2 weeks.